You just said that you want us to know the general trend.
Yeah, so I want you to know how to interpret a Porbet diagram. So what does a Porbet diagram describe?
It'll tell you like the pH of solution and like how it affects erosion of metals.
Yeah. So what are the x and y axes on a Porbet diagram?
What's this pH?
X is pH. What's y? Potential. Okay. What's on the Porbet diagram? What do we put on there?
Lines.
There are some lines.
Metals in different phases.
Yeah. What's usually at the bottom here? Metal 0, right? And so we might have sodium hydroxide, we might have NaOH2, we might have different phases, NaO, something like that. And so depending on what pH we're at and depending on what electric potential we're at, we either have metal or we might have these different phases. Yeah?
So how does this work? I thought that if you have a high pH, metals are less likely to be oxidized.
If you have high pH, well, metals, so it depends on the Porbet diagram, actually. So, but under high pH conditions, acids, right? Are metals stable under acid conditions?
High pH, wait, is it basic or acid?
High pH, oh yeah, high pH is basic, sorry. So under basic conditions, well, it depends. It depends what the potential is. So, yeah. Yes?
What does Na0 mean? Is that just the metal by itself?
Sodium metal, yeah. So what I want you to know about the Porbet diagram, if I give you, say, pH 10 and voltage 4, and I ask you, what phase is sodium going to be in under these conditions, you have to be able to pick that off and say, it's going to be in this NaOH phase. Or if I tell you something about the phase, if I say that NaOH is a stable coating and NaO is an unstable coating, what pH and potential do you want to be at to form a good coating? So I want you to just be able to interpret your way around this diagram. And I'll tell you what you need to know about each of these phases, but you need to know that potential and pH influence what phase the metal's in. Yeah?
When we're talking about phase, we're talking about the whole compound, not just the charge on the metal, right?
Phase, you're talking about the compound, yeah.
Okay.
What phase it's in.
So you don't have to say what charge copper has. You just say.
Well, I don't know. What charge does sodium have in this compound?
1.
+1, yeah. What charge does it have in this compound? +2. What charge does it have in here? +2. So I hope you guys can figure out what the charge is, right? That's easy stuff. I won't ask you any complicated ones, but everyone should know that OH is -1 in this one. Yeah?
So would you say that in this situation, NaOH and NaO couldn't be changed just by moving polarity, or pH you would have to do electron volt EV?
Well, if you're sitting right here, right?
Okay.
And you change the pH, yeah, you could, or change the pH, yeah, you could switch between them. Yeah. So you couldn't go from Na to NaOH2 by changing the pH. You would have to change the potential to cross that line.
And are those the only 4 categories that we have to just know about?
What categories? These 4?
Yeah.
No, you'll get a real Porbet diagram. So Porbet diagrams.
So you need to know how to read it.
You need to know how to read a Porbet diagram. That's the important part, yeah. So I give you a homework problem to practice that, right? Look at one, tell me about what a Porbet diagram means. Other questions? Yes?
How would you find activation energy from the Arrhenius equation?
Yeah. So what does the Arrhenius equation refer to?
The scientist.
The scientist, yeah, so Arrhenius was a person. But what does Arrhenius tell us about a rate?
Oh, based off the temperature.
Temperature dependence of the rate, right? So rate, so let's make sure we get Arrhenius right. That work? Yep. Okay. What's R0?
Initial rate.
Yeah, it's just constant, you know. So the rate is a function of the temperature and the activation energy. R0 is just a constant. What does the CXP mean? E to the whatever, okay? So how do we linearize this thing? Take the natural log, ln rate equals ln of R0 plus ln of negative EA over RT. Ln R0 plus, minus, right? Natural log of an exponential is just the thing in there. Okay, yeah.
On the slideshow it says KT, is that wrong?
No, so this, what's the K here? Boltzmann's constant. So if we wanted to know rate per particle, or rate per molecule, right? We use Boltzmann. But I really want to concentrate on rate per mole, right? We have concentration in per mole, okay? So what does the linear form of this equation look like? What's Y? Y. What's B? What is, what's X? And then what's M? Whoop, sorry. So X equals 1 over T, and M equals negative EA over R. So what do we plot for an, if I ask you to make an Arrhenius plot, what does it look like? Well, what's on the X and Y axes? 1 over T, ln rate. It's like that, and the slope is negative EA over R. What are the units on R? .3 R equals 8.314 joules per mole times K. So this is not E, the slope is not EA over RT, because remember the slope is taken care of by the 1 over T right here. So we don't multiply this EA over R times T. So the activation energy is in joules per mole. So if I tell you that some set of data is Arrhenius, please plot it. Log of rate versus 1 over T. So I would give you a table that has rate and T. I would give you, I might even give you R0 for free equals 3, something like that. And so you could plot this thing out. Yes?
What's the units of EA?
Activation energy is in joules per mole. What's this point right here? Good. We get that right from our linear equation. So you can use Boltzmann's constant if you want for this, but then you need the rate in something per particle, right? Then you have to figure out some funky activation energy per particle. So make sure that your units check out. Usually, oh, let's not go there. What are the units on rate constant? Or what are the units on a rate? Rate is K for first order, right? So a rate is mole per liter times second, right? 1 over seconds, mole per liter. And so if I give you a rate in mole per liter per second, there will be a rate here. You would have to convert that to particles per second or something. You'd have to use Avogadro's number to get out of moles to use K. But we're sticking with moles for this part of the class, and so make sure that you use capital R in this expression right here. So you don't have to convert out of moles. So if you follow your units right, you'll always get, you'll know when to use K or you'll know when to use R. But like I said, you'll have to use R on this exam, so there's no confusion. Yes?
Is there anything special you want us to know about metal dissolution? Because you put that on the thing.
Yeah. What's a good half reaction for a metal dissolving? When a metal dissolves, what happens to it? Turns into ions, right? Which reaction is for metal dissolution? Top one, right? Written right to left. Let's see, is this one oxidation or reduction? Oxidation, right? And this one is what type of reaction? Oxidation or reduction? Great. And so how do we tell?